Welcome, everyone, to our fifth lecture in this series. We have one more next month on April 8th, and that will be the last one for this season. So I'm Dan Halling, Vice President of the Badger History Group, and I'm glad to announce our speaker tonight. He's not a stranger to anyone who has attended these or watched these lectures in the past. Tonight's talk is by Frank Wolf on single-based smokeless propellant production. It's his sixth or seventh, I think, lecture for this group, something like that. And this kind of fills in the whole thing of the propellant production out here, because although smokeless or single base is kind of the first thing that was produced here for and the basis for all the others in a way. Frank hasn't given us his knowledge on that until tonight. So I'm glad about that. Frank is a chemical engineer with nearly 6 decades in the energetic material industry. For those of us who are lay people, that I guess that means kapow. He is now involved in local history as our group's indispensable treasurer and as the historian of his hometown of Mazomanie, about which you have written how many? 8 books now? Something like that? The latest being about Mazo residents who were World War I veterans. It's been my custom when I introduce Frank, who's a chemical engineer, to start with a joke. So here goes. An engineer arrived at work one day. We'll call him Frank, and we'll call his work Badger. And he heard somebody say, "Can you help me?" And he looks and he sees a hot air balloon coming in, low to the ground, obviously in distress. Frank says, "Well, you're only 20 feet off the ground. You're out of fuel." Guy says, "Are you an engineer?" "Yes, how did you know?" "Because you've just given me factual information. It's not helping me in the least." So Frank says, "Are you with management?" "Yeah. How did you know?" "Well, I arrived on the scene. You already had a problem. I haven't done anything yet, and I'm getting blamed for it." I don't know if that's true, Frank, but everybody out there, make sure you mute your mics. And if you're in here, make sure you silence your phones. And we'll give it over to Frank Wolf.
Hey, Fred. Hey, Fred.
I
need
need
my-
papers.
Oh, I took your notes.
Yeah. I want to say thank you, Fred. That's that guy. And talking about this being a chemical engineer versus a civil engineer, my brother Billy is a civil engineer I always say with a capital C, not with a small c. We have different ways of doing things, but that's the way it is. I don't know an awful lot about single base production because it wasn't one of my areas of where I spent a lot of time, but I do know a little bit about it. So here we go. I hope you learn some things tonight and find this the pictures especially being interesting. Also, I want to thank Verlin and Ori because the pictures you see up here, they're the ones that figured out which ones I should use. Content. I want to tell you how we made single base propellant back at Badger in the old days. The way they do it nowadays is not like this, but this is the old days. The lecture content will be something about single base propellant, about the single base here at Badger, what we made in the production record, and then a discussion about a description of the manufacturing processes here at Badger. When there'll be a lot of pictures, and it's got some people in, but we don't know who these people are. Maybe you might recognize somebody. There's a lot of slides, and I'll go kind of fast on some of them, and some of them are pretty busy. What is single base? It is a one-base propellant made out of nitrocellulose, and by single base it means it doesn't have any nitroglycerin in it. It was invented by a Frenchman by the name of Paul Veillet in 1884. It was 3 times as powerful and left little residue as compared to black powder, because black powder is a dirty, made out of charcoal and sulfur and potassium nitrate. So this new stuff, this single base, was really much better. And single base propellant is a cylindrical with diameters from 1/4 of an inch to up to about 1 inch in diameter, and with lengths up to 4 inches. The size is a very important parameter of single base propellants. Badger made over 30 different types of these single base propellants over the years. Things changed from one era to another, so they made a lot of different types of single base propellants. Badger's single base lines were built in 1942 and 1943, and the process is a batch process. That's compared to a continuous process. Nowadays, the process is continuous, but back then it was a batch process. And there are 4 lines, B, C, D, and E. People have asked me what happened to A. Verlin and I have discussed this, and I don't know. There's just no A. There might have been a room over there for A at one time, but no A's, B, C, D, and E. And there's an awful lot of buildings. Here's a picture of small-sized single-base propellant. It is loaded into the back end of a cartridge and a bullet, or is in the bottom of a gun. And this is what the explosion makes the bullet move. Single base propellant ingredients. Here's a listing with a concentration depending on what type of single base propellant we're making. Nitrocellulose there is the base, 80 to 98%. Then there's a deterrent, dinitrotoluene, and that's added to control the burning rate. You want it to burn at a constant rate, constantly. Dibutyl thiolate is a colloid, and that's added to help form this lacquer solution that forms the grains, to make sure all the part of a grain is the same concentration of ingredients. Then there's a stabilizer, diphenylamine, and that's added to prolong the life of the shelf life of the propellant. Fred there, he was telling me this last week about somebody that bought some propellant that was made at Badger in the 1940s, and it was still in the same box, and they were wondering whether they could still use it to load into shells. And I can't believe it was 50 years old. Oh, wait a minute. Yeah, 50 years old, and they still might be using it. Now, that's an awful long shelf life for propellant. I told him he should be careful. You never know, because here's a single base flow sheet. Can you all see that? Yeah, it's all really mixed up, and it's very complicated. You'll see a lot of recycle lines. You see over here, recycle. From here, it goes back and starts over again, and here it goes back and recycling in here. Very, very complicated. So let's make something a little bit simpler so we can, because I'm not going to talk about this one. That's that takes too long, and I don't myself know exactly what some of the lines are. There, that's much simpler. 4 main process parts. Colloid or mixing, extrusion where you form the propellant grains, then recovering the solvents from the grains, and then blending and batching and packing out. You can see the flow sheet. Here's the nitrocellulose coming in, and then you're mixing it with alcohol, ether, and these other additives I just mentioned, and extruding it. Then you solvent recovery where you're putting water and inert gas to get these solvents out, and then blending it together with graphite to make the final propellant. Much simpler than that other one. Here are some of the single base propellants made. 30 caliber for the M1 rifle, 105 millimeter rifle, 105 millimeter howitzer, 90 millimeter gun, 75 millimeter gun, and then they also made single base for the big 16-inch diameter guns on the ships. There were also other types from this that were made. Here's some of the single base ammunition, some of the bullets. 30 caliber machine, 30 caliber and sidearm, a 30 caliber M1 rifle, 50 caliber machine gun, and a 20 millimeter cannon. And right back down here, you probably all know, this is where that propellant goes, in the bottom of the shell. Badger single base production. How much single base did Badger really make? Well, during World War II, they made 258 million pounds. During the Korean War, 236 million pounds. Then in the 9 years of Vietnam, they made even more. 315 million pounds were produced. During this whole time frame here at Badger, we made 800 million pounds in those 19 years. And that's an awful lot. That's a lot of truckloads and rail car loads. But that's still only about a quarter of what Badger's total capacity could have been, of 190 million pounds a year. And even during the peak production times during Vietnam, there were only 2 of the 4 lines. It was usually B and C that were operated. The other lines, they were there in case we needed it. So Badger really only operated at 25% capacity. It's the single base area at Badger is shown here in green. Pretty good size area. And then in the yellow, that's the ball powder plant to the south of the single base areas. See, here's the various lines. Now here's B. I guess A is over here somewhere, but here's B and C and D and E. And then here's ball powder. Here's a picture of Badger in about 1952 or so. Here we're looking towards the east. Here's the lake. And here's C going this way. And here's B line going this way. Here's the big powerhouse, and here's the old acid areas. You see these are some of the buildings. Here's the center part, and up here's this must have been taken in the 80s, because here's the new acid area. Here's the old powerhouse, second powerhouse out by Rocket. Rocket's over in this area. Oh, this one was taken about the 1953, 2 or 3, somewhere in there, because here's ball powder. Here's all four BC D and E single base lines. Now we're looking from up on the bluff, we're looking towards the south. Here's all the solvent recovery buildings in BCDE lines. All look the same because they all are the same. Then there's the water dry buildings, whole bunch of them all lined up. Then the air dry buildings here, here the coating and the blending buildings. Here's the center, the administration buildings are up here. There's the pack out, single base can pack out buildings, and they're in this area right here. Whoops. Right here, pack out buildings. Here's the second powerhouse. The cemetery is right in here, I believe it is. Here we're looking from up on the bluff, looking towards the south. The rocket area is all these buildings back in here. Here are some more area buildings that I wanted to show you looking towards the bluff from the south. These are the alcohol ether buildings, which are part of the single base. Here's the bluff up here, and here's the old coal pile. Remember the old coal pile? And here's the rocket testing area, where the ballistics area where they fired into a tunnel in the bluff. Okay, the dehy process, the first step in production. Here the water is removed by displacement with alcohol and ether. The wet 30% moisture nitrocellulose is delivered to the dehy house in Telfer tubs. The alcohol is pressed out and the nitrocellulose blocks sent to the mix house by buggy, and they called the buggy the coffin buggy. There are 12 presses in each house. They pressed these blocks, they pressed them into 50-pound blocks at 300 psi, pounds per square inch pressing. That's what a dehy press looks like. Each set of doors has a set of pressers in between them. Between these various barricades here, there's a barricade here. One-story building. There's a set of the presses, what they look like. Two presses side by side. Here's where you pressed, this was coming down and pressing into this bottom part. Dehy press. There's a picture of the coffin buggy. I wish we knew the names of these people, but we do know that that's the coffin buggy. That's what they carried. They carried these pressed blocks. They're going to the mix operation.
An angel buggy?
Nope, this is not an angel buggy. This is a coffin buggy. An angel buggy is nitroglycerin area, but it's sort of the same idea that coffin, angels. If you goes off, yep. Mix house. Here all the ingredients are added all together into a Sigma blade mixer. The mixing operation plus the solvents colloids the nitrocellulose and makes a very homogeneous mixture. But since this mixture is not complete, the mixture is macerated. That's another type of mixer to complete this doughy, trying to get it all together being the very same all over. Each of the mix houses has 6 mixers in it, and 8 macerators. Each batch is mixed for 30 minutes, and then it's macerated for only 3 to 8 minutes. There's a mix of macerator with 2 ladies there unloading it, putting it into tubs. You see they all got special clothes on, and up here you see fire protection system, deluge system. You see these tubs here are on top of a little cart. Here's another picture of the unloading them. The mixer macerator house. This is the mixer. And we don't know who these 2 gentlemen are, but you can see they got their safety glasses on, but they don't have a hard hat on. And that indicates that this is 1940s, Verlin.
It didn't be Vietnam. They didn't need a hard hat.
Yeah, that's right. That's right. A hard hat might fall off. You get into the wrong place. Next operation is a pre-block house. At this stage, the powder is in lumps. It's got air pockets with it. And the powder is pre-blocked to eliminate these air pockets and get the powder ready to macaroni and or final press. Each press house has 6 of these pre-blocking presses, and each press is pressed at 330 pounds per square inch at 120 Fahrenheit. And it makes these blocks into 12-inch diameter by 15-inch long blocks. Pre-block press house. The material then needs to be made smooth and foreign material removed for this final pressing. The pre-blocks are delivered in a transfer chute to a macaroni press. The macaroni press is named macaroni because it looks like a macaroni tube. The powder drops down from what they call a elephant trunk from the macaroni press automatically into the final press. 3 houses per line, 2 macaroni presses, and 6 final presses. The final press takes about 30 seconds at, again, 330,000 PSI and 120 degrees Fahrenheit. Final press house operations, you want to powder is prepared for cutting. So it's pressed into these strands. The pre-block powder is delivered in these tubs, taken into the cutting house on a buggy, and there are 3 houses per line, 10 presses per house. The line capacity is 160,000 to 190,000 pounds per day, and that's a 24-hour day. And there's a press house operation. You can see the strands of propellant coming from the final press. Here's the final press up here, and the little white strands coming out. And you can see how they look like little strand of macaroni, and that's why they call it the macaroni press. Here again, special clothes, special shoes, and up here is the sprinkler systems. Cutting house, the strands that you just saw there that are cut into proper lengths. There are 12 cutting machines in each house. The line capacity is 180,000 to 300,000 pounds per day. That sort of depends on what size of grains you're cutting. Picture of manually feeding these macaroni strands into the machine. So they're moving this way into the machine, and then back in here, you got revolving blades that are cutting the long grain macaroni grain into grains. Here again, eyeglasses, special clothes. I would have thought they probably would have had some kind of gloves on, but I don't see them any gloves here, but special clothes. Next step, the cut powder is delivered to the solvent recovery house, recovery tanks to remove as much solvent as possible. Heated inert gas is circulated through the powder to pull off these solvents. Recovery takes about 24 to 60 hours at 150 degrees Fahrenheit, depending on what type of grain you're talking about. And there are 15 houses per line. Each house has 5 10-foot diameter by 8-foot 3-inch tanks in height, and each tank holds 7,700 pounds. And the line capacity with all these houses is 550,000 to 850,000 pounds per day. That depends on what kind of propellant you're making. There's a solvent recovery house. See a lot of these safety chutes. That's a 2-story building, barricade around it. This is where the propellant comes up in an elevator, goes onto the second floor and dumped into the tanks, brought out on the bottom. And there's a tram system here that you can't quite see, but see the big chutes that people, if there's a problem, they run out and run down there and slide down the. One might think that that's fun to do, but it's hard on the bottom, sliding on that. Here's another shot looking at a barricaded house with several escape chutes. Probably easier to slide down this one where it's got a little snow in it. But you see a 2-story building, barricade around it. Here's that elevator. In the tram system here, see a tram here where they're hauling these buggies with the Telfer tubs on. Solvent recovery tank. Picture of the bottom of the tank with the powder buggy. There's a 10-foot diameter tank. Water dry operations. The very last traces of solvent are difficult to remove, and for this reason, the final removal is done by soaking the powder in hot 150-degree water in water dry tanks. That's where this word water dry, sort of oxymoron kind of little word. Water dry. Moisture level is dropped from about 5% solvent to 1 or 2% solvent. And here, this recovery cycle takes anywhere from 4 to 12 days, quite a long, indefinite period. There are 10 houses per line, 2 16-foot diameter by 9-foot tall tanks, and each tank holds all the way up to 50,000 pounds. And the line capacity here is 300,000 to 1 million pounds per day, all depending on what kind of powder you're making. There's a picture of the water dry house. Again, a 2-story building, partly barricaded. Tram system here in front of it where they unload the Telfer tubs. The escape chute. Here's the water dry build tank itself with a cover that's a flexible cover. Air dry operations. Here where last moisture is removed by blowing hot air through a tank, dropping the final moisture from that 5 down to 0.5%. Air recovery is at 130 degrees Fahrenheit at 3,500 cubic feet per minute of air, with a drying cycle, again, variable from 5 to 12 hours, depending on how fast things dry. There are 5 houses per each line, and it has 2 10-foot diameter by 9-foot tall tanks. And here each tank holds 10,000 pounds. And the line capacity is variable depending on operations, which kind of propellant you're making. 550,000 pounds to 1,000,000 pounds per day. There's what one of them air dry houses look like. Now all these buildings sort of look the same. They all got this barricade around them with chutes on. So you got to be kind of hard to pick out exactly which one you're looking at. But here's the air dry house. And again, you have the chutes coming off the second floor, and here's the elevator shafts where the propellant is brought up and brought into the building. There's the bottom of the air dry tank. You see barricades on each side of the buildings of the tanks. And here's a picture of loading an air dry tank. All these little grains need to be taken down to 0.5% moisture. Oh, okay, now we sort of got a finished product. But to make large lots of these uniform propellants, small and equal amounts of propellant are taken from many batches. We've done up to now it's all done in batches. Now we're going to blend it together to make a big batch of 50,000 pounds or so, and blended to inform very uniform moisture and content and ballistics. Because when they put this propellant into a shell, every shell has got to be exactly the same as the 1,000 before that. So you want to have the propellant to be exactly the same ballistic wise. The air dry powder is delivered in buggies on a tram and blended in 5,000 pound charges in the blending barrel. The batches are blended 5 minutes and then dumped into 85-pound bags. And the line capacity is 1.5 million pounds per day. And here again, another barricaded building, up a little bit higher. Here's the tram system bringing the powder in, up the elevator, across into the building, dumped in the tanks. Chute coming out. Here's sort of the office for the operation, because people are normally not in here when they're doing their blending, because that's when something might happen. There's a blender barrel. This is the back side of the barrel. And I got into the habit of calling this type of blending barrel a sweetie barrel, because the same kind of barrel is used to blend candy, put sugar on candy and stuff like that. So this is a sweetie barrel to me. And here's a picture of weighing out of that sweetie barrel into a chute into 85-pound bags. You can see a broom back here for keeping the floor clean. You don't want to have any of this powder laying around on the floor. That's when things happen. Final blend house operations. To ensure that you really got a uniform batch, it's blended a final time. Pre-blend powder is delivered in these bags you saw on the tram, and blended in 5,000-pound charges in a blending barrel. The blending is for 5 minutes, and then it's dumped into a tub system to get it over to pack out. And the line capacity here is 720,000 pounds a day. And here's a picture of the final blend barrel. You can see it's zigzag, a little bit different shaped blending barrel. This is the final blending barrel. And this here is the loading. Then it swirls around and goes back and forth, different sides. Can pack operation. Packing for shipment, so you can send it to a loading plant. The blended powder is delivered in this tub system automatically from the final blend house. The powder is screened in here and is weighed into a shipping container. And here the line capacity is 720,000 pounds per day. Another barricade building, the pack out house. Over here is where it was final blended, goes through this little system, overhead tram system into the final pack out building. Here again, you got a chute, and then here is where they load up the packed, and usually in boxes or cans. I wanted to show another major operation of the single base. It's called the Activated Carbon Recovery House. Here is where we take this ethyl alcohol and ethyl ether that we used in producing the solutions in the lacquer. That's where that's recovered. And it's a very big building. And here's a line with these solvents coming in. And here I wanted to show you a sample of the now old-fashioned control panels from the 1940s. There is no computer control here. There's all kinds of control wiring and so on behind here. A lot of little air lines. And Verlin could probably give you a whole lecture all day long on what goes on here. But all I know is that this is an old-fashioned control system. No computer control here. The direct labor to make large amounts of single base takes a lot of people. It takes 170 people per shift, per line, to make propellant on a line. And that equates down to about 70 hours per 1,000 pounds of propellant. A lot of people. Now remember, this 170, that's one line. And there are people working at all these different places. Like all these people where they're mixing and pressing and cutting. You saw the pictures of all those people. A lot of people. And then when you first put nitrocellulose into the single base line, it doesn't come out as a final product until something like 2 or 3 weeks later. You see, a lot of those operations took days to complete, and sometimes it takes almost a week in the solvent recovery area, depending on how much solvent you had to remove. So this is a long process to making nitrocellulose or making single base. 70 hours per 1,000 pounds. There are an awful lot of buildings involved. And here's a listing of them. Some of the minor buildings, like restrooms, are not required. So if you actually count all the buildings that show up on these maps, there's more than that. But these are the major process buildings. And you can see there's an awful lot of, and you saw the pictures, an awful lot of these solvent recovery and water dry buildings. Just a lot of buildings, a lot of space. 280. And that's the end. Thank you. Are there any questions?
All the product on these trams, what happens when it rains or snows? Were they enclosed or what?
Everything's usually pretty well covered up. Yeah, so that if it rains, they won't get wet. Because as you would probably know, if you get it wet, well, that's more water you got to get rid of. It's all wet. And wet powder doesn't work very good. Yep. And I got the feeling that if it really rained hard, things sort of slowed down. A lot of this transfer, they wanted to do it right away, but it could wait a couple hours. Because some of these operations are gonna be several days if they complete it anyway. Yep,
So various processes of solvent recovery, what were they removing? What form was it in? What happened to it? How was it transported to some other, to be reused or whatever?
Would you mind repeating the question, Frank, so Zoom people can hear?
I'll go back to the little flow sheet the way at the beginning here. There was a question of the solvents removed and the what happened to it.
Yeah, what were they?
Well, you see here the alcohol and the ethyl ether that was put in when the mixing to make so it would get into to make it into a doughy thing. And then that's carried along through extrusion, and the solvent recovery is where you take out the alcohol and the ethers, recovering it. And then you recycle that back and reuse the alcohol and the ether again. So you keep reusing the alcohol ether. That's cycled. That's one of these lines here. You see this line over here? That's all this solvent going back to reused again. Or is it over on this side? Yeah, it's over on this side where these lines here where our solvent is being recycled and reused again and again and again.
Are they moving this in tanks? It's in liquid form and they're moving it in tanks and then these have to be.
It was pumped. It was pumped, regular pumps. It's part of all these, if you would have seen, the Badger, it's hard to see on some of the pictures, but you see pipelines all over, a lot of pipelines. Most of the pipelines are, steam lines, but a lot of them are also product lines, like alcohol and ether lines. Yes.
Yeah, so coming out of the macaroni press or whatever you call that, where you have spaghetti-like strands of this coming out, was that done in a particular size, or were there multiple sizes depending upon the particular type of powder you were making, or?
They were multiple sizes depending on what kind of propellant you were making at that time. So there was 30 different types you could have had made, all the way from about 1/4 of an inch, and 1/4 of an inch is rounding it off, because it was to the thousandth of an inch, their diameters, very precise. And then it would be made to a certain length. And I didn't really touch on it much, but there's also little holes. You got this cylinder that's got a bunch of holes in it that are different little diameters also, depending on what kind of propellant you're making. So it's quite a complex little piece of macaroni. More than just one little hole through the middle. And all that depends on surface area and the ballistics.
We have 2 Zoom questions. John asks, did they make single base year round? Did they have trouble with the tracks being outside transporting product from building to building in the snow?
The question was, did they make propellant year round? And the answer is yes. Year round, 7 days a week.
Snow or rain or?
31 days a month, all the time. And maybe they slowed down a little bit if the snow got deep or it rained a lot, but it was year round.
And then how many people worked on one line for one shift?
That was that 170.
Yeah. And then how long was a workday?
There we'll get to
Here.
170 people per 8-hour shift, an 8-hour shift. None of this 12-hour stuff. that'd have been pretty tough on people doing this kind of work for 12 hours a day. That would have, I don't know if Fred,
Uh, At what point in that process was it more likely that something was going to happen that you didn't want to? Like an accident, a fire, explosion.
well, to me, the most dangerous part are these blending operations. Because the rest of them are people were very careful about sparks, wearing proper shoes. The tools they use, like the wooden mallets, the wooden shovels, things like that, so he didn't spark. He tried to eliminate that spark. But single base itself is pretty pretty safe as far as sparks go. It's not like double base. So the safety of a single base production is, to my way of looking at it, is much safer than double base, the rocket area. So you're pretty safe. There's only a few operations that are got to be a little bit careful about. Like with the presses, the people are not in the bay with the press when the press is pressing. You leave. You load it up, get it all ready, then you leave. You go outside the concrete barricade, so that when it actually presses, which that's when something might happen, most likely to happen, you're not there. Do you have, Mike?
In the mixing and the blending, what are the containers, the tanks made of, and what's whatever is mixing them inside the agitator or whatever, what's that made of?
Oh, almost all the tanks that I'm aware of are 304 stainless steel, which is a pretty good stainless steel. They don't have, no, there aren't any copper or titanium in that. That's acid area. It's pretty well just stainless steel. Or if it's like steam tanks and that and air tanks, it's mild steel. But where it comes in contact with powder, it's stainless steel. Oh,
I was in Roads and Grounds during the production years, and we were in charge of unloading the railroad cars into the warehouse at the beginning of production. The cotton in bales and wood pulp in giant toilet paper.
Yep.
They range, I don't know, 700 to 800 pounds, depending on whether they're Canadian or Weyerhaeuser brand. But that's as close as I got to the beginning of production. 10 years that I was down there.
Yep. Paper and rolls just like they're going to make a printing newspaper.
It was the paper was almost 1/8 of an inch thick. Pretty close to it.
Uh-huh.
And of course, that got unrolled. Unrolled and went into an oven. And this went, I don't know, 7,500 feet. It came back. And then it went again. To get the moisture content down to, I guess, 0.
Uh-huh.
Yeah.
And when you talk about a paper roll, it's a big one, isn't it?
Oh, yeah.
6-foot diameter.
Say that's 700 to 800 pounds, depending on whether it's Canadian or Weyerhaeuser. And there might have been other brands there too, I don't know.
Uh-huh. That's cellulose.
Yeah.
Mike?
So when you're making the grains and you're making the macaroni, how do those little holes get in there? How do
That's
you
in
make
the
sure
press, during the press. where you saw those macaroni things coming out, you can't see it, but depending on what kind it was, there's holes in those
So that's just, the holes just form when it's being pressed.
during the extrusion. Well, it's very precise diameter, dimensions, very precise. And that's where you have a lot of laboratory work to make sure everything stays as close as exactly the same as you can make them.
So-
And they're talking about thousandths of an inch dimensions, very precise.
But the pressure that you're creating those under must be critical then.
Yes, yes, yes.
And one more question. When you're adding the deterrent, is that you're adding that to the grains after they're formed so it coats them on the outside, or what is?
No, it's added in the beginning during the mixing. All those ingredients, except for graphite, is added right at the beginning. And the graphite, that's at the end to make it slippery and be able to smoother to moving it around. It flows easier.
Oh, you have another question. Oh,
That's a big one, and that's the holes.
This is one of the dyes, isn't it? Verlin?
Yeah.
This is the dye, isn't it?
That's half of a die. That's the part that puts the holes in the length of the grain.
And this is a fairly good sized.
Yeah, that's
Uh,
the biggest, that was the biggest we made.
You can see all the little holes?
Frank, can you hold it a little lower so the people on Zoom can see it?
Okay.
The camera is like right at the top of your, up to the
don't
center.
have to
There you
go
go.
slow.
Perfect. That's great. Yep. They can see it, so you can hold it. Perfect. That's good.
Did you have a fine?
Yeah, hang on. There are two more questions. One, both from Carolyn Dahlman. The first is, and this might be another talk entirely, but could you explain the initial nitration of cellulose? And then I guess her other is,
That was one of my initial talks,
okay. We'll put that up on YouTube soon.
but that's a 45-minute talk.
Okay.
How you make,
And then Carolyn noted that lab techs measured the diameter of grains and the width in the holes of the grains. It was labor intensive work. She comments.
but it's extremely important
Yeah.
because you want to make sure you can't have ammunition that sometimes it goes a mile and a half and sometimes it only goes 3/4 of a mile. I mean, it's got to be very, very precise. And with the way these automatic weapons shoot nowadays, I mean, everything's got to be very exactly the same. Otherwise, the rifle doesn't work. It blows up or because. Yep. Any other questions? Thank you very much.
Well, thanks, Frank. It sounds like we perhaps have some more lectures from you in the future based on the questions. But when I was doing some research back when I was teaching history, I remember being struck by the importance of smokeless powder compared to black powder. And I think the first time that became apparent was in the Spanish-American War. We were still using black powder and the Spanish were using smokeless. And our soldiers couldn't figure out where they were shooting from because they couldn't see the characteristic, giveaway puff. And I think that was perhaps the first war that smokeless was used. And then the American Army, which prevailed in spite of that, decided they better make some of that stuff. So anyway, that's just my little side. So next week or next month, April 8th, Mike Gock is going to give a presentation on farming from the era from about 1900 to the time the plant took over. And that should be very interesting in a very different way than tonight. So I hope you either come to us again on Zoom or come to the museum to see the last in this series. And we'll be starting up again next fall, September probably, when we'll be starting our next round.